Hello, Vinay.
Hi, sir.
How are you?
Good, sir. How are you?
Oh, pretty good.
Yeah.
Hi, Abraham.
Hello.
Hi. All right, how are you doing?
Oh, very well.
Oh, good. Good. There's Dick.
Yourselves?
Oh, I'm doing well. Hello, Dick. Okay. And there's Ujwal. Actually, I'll have Ujwal introduce himself when we get started here. Hi, Ujwal. How are you?
Fine, sir. Hi, hello, everyone.
Yeah. Glad you could make it. Okay. Well, let's get started. And if more people come in, we'll say hi to them as they come in. So welcome to our current version of the DevoWorm ML. We have a member, he's a new member to this group, but he's worked in DevoWorm before, Ujwal Singh. Why don't you introduce yourself?
Hello, hi, everyone. Myself, Ujwal Singh, and I'm an undergrad student at IIT Delhi. And I'm basically interested in machine learning stuff, and I'm studying about how we can implement it to biology.
Okay. Ujwal, actually, for those of you who, I think all of you saw the Digital Basilaria presentation, and he's one of the people, of course, who contributed to that work this summer. So his interests are deep learning, and he's very interested in a lot of things. So he's going to be, I guess, welcome to the meeting. So I guess the first order of business, does anyone have any questions or comments? Anything they'd like to, any news they'd like to share? Okay. Looks like Dick had technical difficulty, so he's going to log out and log back in, hopefully. So Vinay emailed me this week, or he slacked me, and he asked if he could present on some, or profile some educational resources.
Yes, sir. I went through those resources. Then I came to know all of the TensorFlow tools and how people are using those TensorFlow tools in their respective companies to solve specific problems. So I made a summary. Like I extracted what I found interesting, and I made a presentation to present it today.
Okay, sounds good. Can you share your screen?
Yes, sir. Please give me a minute.
Okay. Can you hear us?
Yes, now it's fine.
Okay. Okay.
So, yeah, everyone can see my screen, right?
Yes.
Yeah, so today I'm going to discuss about the applications of machine learning, like in the research field and also in the industry field, how people are using machine learning with the help of TensorFlow. So let us start. I want to give a brief introduction of all the major TensorFlow tools that are available today. The first is, of course, the TensorFlow core module. You can learn more about the TensorFlow core from tensorflow.org. It provides a low-level module, which is the tf.nn module, and also a high-level module, which is the tf.keras module. So what this does is that in tf.nn there are convolutional layers, there are batch normalization layers, there are max pooling layers. All these layers are already implemented in tf.nn. But in tf.nn, it's more level, it's more low level, because you'll have to take care of all the parameters also. For example, let's say for batch normalization, you need to give your input gamma and beta values when you're using tf.nn. This is for, of course, this is for advanced users, like when someone wants to experiment with a new kind of architecture or new kind of deep learning architecture, then tf.nn or tf.layers module will be very useful. If that's not the case, and if someone wants to make a quick prototype of what they have in mind, they can use tf.keras module. It's a high level module which operates on tf.nn. Like, it automates lots of stuff, and the user will not need to worry about all the parameters involved. So this API, we can TensorFlow is providing in 3 versions, like a sequential API, a functional API, and a subclassing API. It's generally advised for beginners to use the sequential API, like for a standard examples. Let's say we want to classify MNIST datasets, and we want to get a hold of how machine learning works. Then we can go with the sequential API. And then if we want to experiment with pre-existing models, like if there is there is already an architecture, let's say convolutional neural network, and if we want to give multiple inputs and extract multiple outputs, then we can go with the functional API. Like, this API gives us more flexibility on how and gives us more control over the framework. And then the subclassing API, it is advised for the advanced users, like researchers who want to create explore new experiments, like creating a new neural network architecture. So TensorFlow provides all these APIs. I want to show small examples of each of them. So this is the sequential API here. This is a standard MNIST training code. Like, we could just import tf.keras.datasets.mnist into this, and we can split them into xtrain, ytrain, and xtest, ytest. Here, xtrain are the images and ytrain are the labels, like the number in the image. Let's say we have images of handwritten datasets, and this ytrain will contain the numbers containing the images, like those will be the labels. So here you can see the sequential API here. This is how we would implement a sequential API. tf.keras.layers is a high level module, and we can add those flatten layers, dense layers, dropout layers, and again dense layers. Like, we can put any kind of combination here. So for the standard use cases, this sequential API will work very well. But when do we need functional API or subclassing API? First, the problem with sequential API is, if I wanted, there is only one input shape here, right? So if I wanted to tweak it a little bit, and if I wanted to take inputs to the model from 2 sources, and also let's say if I wanted to get 2 outputs from a single model, let's say from one model I want to get the coordinates of the face and also the yes or no value of face found or not. So that will be 2 outputs, right, from one machine learning model. So for such kind of use cases, we can use the functional API. This is the functional API here. We can use this because we can get a great flexibility because of this line here. Here we can specify the inputs and specify the outputs after connecting the layers. So when we specify inputs here, we can it's highly customizable in this API, and also the outputs as well. And then the subclassing API. This subclassing API is used for let's say we want to it gives even more flexibility for us. It gives us more control of how we can arrange the model. Let's say if we want to uh, add layers dynamically, or if you want to compute the output shapes, if you want to define a new network architecture, like there's a CNN, there's a RNN, and if you want to define our own architecture, then this subclassing API will be very useful for us. So basically, the TensorFlow gives a sequential API for novice users, functional API for professionals, and subclassing use API for researchers who want to explore in deep learning, explore deep learning. So the second thing that TensorFlow Extended provides is that TensorFlow Extended. This came into existence when they thought about how like once we train the data set, like once we train the deep learning models, they thought how these can be these models can be served across, like expose it to the world. How can they make sense of what the machine learned, or how can these models can be served to the world effectively and efficiently. So then they introduced the TensorFlow Extended tool, where it takes care of like right from the start, right from the data preparation to model with model production. It can take care of everything, like let's say configuration, data verification, data collection. Like this tool provides methods to take care of all these serving infrastructures and also process management tools. Like these are all important because whenever we trained a deep learning model, and if we wanted to serve it to a massive scale of people, like if our servers are getting heavy load and all, then this TensorFlow Extended will be very useful for us. And within TensorFlow Extended, they introduced TensorFlow model analysis. So this is a tool where we can get insights of what the model has learned. Let's say we can change the metric, and we can see how the data learned on the entire data set, and also we can see how how the model learn like how the model weights got updated at a specific subset of a data set, and we can explore how the data changed the model over time. So this is the TensorFlow model analysis, this toolkit. We can explore various insights from this, like we can get the which feature has been dominant at which point of time during the training, and which factor is affecting the model, model weights heavily, and more stuff from this TensorFlow model analysis. And then they also introduce a TensorFlow serving. TensorFlow serving helps us to expose our models to the world efficiently. So this is best this best serves our purpose when we want our model to provide outputs to many users at a single time. So this is how the architecture is. This is the client. This is a user requesting a model, inference from a model. Inference is nothing but the output of the model. So let's say we have we have multiple versions of a single model. Let's say we trained our model for the first time, we deployed it, and then we trained the model, we got new data, we trained the model, and we deployed another version. Previously, without this TensorFlow serving, like it would be difficult to maintain two versions in the same server, like two versions of the same model in the same server. So with TensorFlow serving, deploy any number of versions without affecting the previous versions in the server, and then the users can fetch the details from any version number of the model. They'll specify a model version number, and then they'll get the output from that version of the model. So this is how it works actually inside the TensorFlow serving. They'll first whenever a client requests the output of a model from the server, first the source will detect the latest version. If the user did not specify the version, so source will try to give the latest version to the user. First, the source fetches in the file system. It will search the latest model, latest version of the model. It will fetch that model, and it will create a loader for that. A loader is nothing but it's a structure which helps the model to be loaded into the main memory of this server, and then so this source will tell the dynamic manager that it has requested for a new version. Then this dynamic manager, what its job is to, the dynamic manager's job is to make sure that the server is up all the time, like it's working all the time. So whenever the source tells the dynamic manager that a loader has been created for the model to be served, then the dynamic manager will make a decision. Okay, is there enough memory to load this new version, or do I have to remove the older versions from the main memory? Like it has a set of instructions embedded into it, and then it will, based on its priorities, it will decide to whether to accept the request or to deny the request. In case if the request is accepted, then this loader will be directly given to the servable handle. So what a servable is nothing but clients use these objects, like servable is nothing but an object. These clients use these objects to perform a lookup. Like let's say I want two outputs, like two outputs from two different versions of a model at the same time. Then this servable handle will specify the dynamic manager, will specify that to dynamic manager, and then the process will be transferred to here, and then finally the client will receive. So basically, TensorFlow serving is very useful when we have multiple versions of a model. If a user requested for one version of a model, and somewhere across the globe, other user can also request another version of the same model, and also this will be very efficient. This architecture is said to be very efficient. So that's how TensorFlow serving helps us to serve multiple versions of a single model in a single server. And TensorFlow.js. One second. In this TensorFlow serving, in this TensorFlow extended, I found out a use case where few people try to like this TensorFlow extended provides an end-to-end workflow, right from the collection of data to getting the output from the model. So what few people did is that they tried to analyze psychophysiological data from the human body, and then they connected this workflow to the GCP model, Google Cloud Compute. They trained their models in the Google Cloud Compute, So what their aim is that from our body, which for which a device will be attached, from there we'll be getting the data of our physiological signals from our body in real time. Okay, so so the model will be continuously getting data, and then it should make a prediction of our affective state. So that's one use case that few people used TensorFlow like the methods from TensorFlow extended, and then there's TensorFlow.js. So TensorFlow.js is nothing but a Java, like it enables us to do machine learning right inside, right in JavaScript and right in the browser itself. So we can write neural networks in JavaScript, or we can convert the Python models and run them in the browser as well with the help of TensorFlow.js. And also we can load pre-trained models and retrain them in the browser itself. And we can deploy our models in pure JavaScript, like without using any external any frameworks, like any Python frameworks or PHP or anything. So there are a few advantages here. Like why it's often a question like why not just deploy the model into a server and get and send the requests to that model and get the response from the model. So why they use Tensor? Why the advantages of TensorFlow.js are, first of all, there's no setup required. Like you don't have to install anything. There's a CDN link for TensorFlow.js. You can just copy paste that into your HTML code, and then you can use all the TensorFlow Keras layers or convolutional layers or your recurrent neural net layers right in the browser itself. So there's no setup or nothing is required. And the second point is privacy. So when we want to train our let's say we have a huge data set and we want to train a model on that. So on our systems it will be a very slow, because we need, for very huge data sets, we need specific servers which can do high computations. So we often need to send our data to that server, and then we need to train it there, and then we need to get back the results, right? So if in here it is not the case, because we can train the models right in the browser itself. We don't need to send we don't need to request the server to every time to get the results. Like let's say I want to segment an image. So the first step would be I would send the image to a server, and that server will feed my image to the model, and then the output will be given to me as a response. In this case, we don't need to do that because there is no server here. We can do it entirely in the browser only. And let's say we want to do some real-time video processing. Let's say we want to do real-time video segmentation. If we implemented this as a REST API or a server model, so we needed to send each frame of the video to the model, and then the model will segment that image, and then it will send a response back. So there's a huge lag over there, because we need to send data and receive data. Here in TensorFlow.js, we can directly get the inference in the browser itself, like the inference of the model. So those are the main advantages. And also TensorFlow.js can make use of the GPU on our system, which and also it supports WebGL. So it's okay to train models in the browser itself. And there's a nice example that Google provided when they presented TensorFlow.js. Let's say if there's a game, if there's a Pacman game here. So what they did is that instead of this up, left, right, down controls, they wanted to make the machine understand the signals without these buttons, without this up arrow, left arrow, right arrow, and down arrow. So what they did is that for each arrow, the user would be giving a pose. Let's say if I put my chin up, and if I click some images, those images will be associated with up arrow here. And then if I turn my head right, and if I click some images, and if I associate with those images with the right arrow, then the model learns to understand that whenever we turn right, then the model understands that we are actually trying to click a right arrow. So basically how this works is that first we need to feed in our images. For the up arrow, we need to pick a specific posture of ourselves, and we need to feed those images. The same for left arrow, right arrow, and the down arrow, and then we would train the model. So what this training does is that we'll be giving some examples, right? Let's say I gave a 10 different images of me raising my chin up, and then I told the machine to associate it with the right arrow, top arrow. Then during this training, the model learns to, like, in the real time, when we are testing the model in real time, whenever we put our chin up, then the model recognizes our posture in real time, and then it detects that we are actually wanting to click a up arrow. So then it would cause the Pacman to go up. Similarly for the right arrow, left arrow, and the down arrow as well. So all this is possible. All of this is possible because of TensorFlow.js, only because this entire thing can be run in the browser itself. So whenever we try to train the model, it will take these images that we fed as examples, and then after the training has been completed, when we actually play the game, it will be taking the video input of our face, like of our posture. So whenever we do a chin up, it will identify it as a top arrow, and then it will cause the Pacman to go up, or respective actions. So this is a nice example of how TensorFlow.js enables us to do uh, real-time training, or real-time predictions of users posture. So that's basically about TensorFlow.js. Then there's also TensorFlow Lite. So this is specifically designed uh, for mobile phones, and also for embedded systems, like, let's say, Node MCU or Raspberry Pi, and low capacity machines. So why is this needed? Why TensorFlow Lite is needed? Let's say we have first of all, what are the advantages it gives, and why is it important? So it makes edge computing possible. Without internet, we can actually use machine learning right in our hand. Like, let's say we trained a model in Python, and we converted it into a TensorFlow Lite model, and then we deployed it into our Android phone or an iOS phone. We can directly do our task. Let's say we want to predict. Let's say we want to classify leaves or plants. Plants are not available near any city locations. We'll have to go to, right. So during those times, when the internet is not available, we can convert it into a TensorFlow Lite model, and we can deploy it into our phones. We can go to that remote location, and we can just like we can take a picture of that, and then we can get the output without having to without any need of a major advantage in the electronics industry as well, because because our gadgets that we use be more those can become more personalized for ourselves, like when the model can learn right from without any data connections, without depending on any further without requesting any server for data. So this is an example that they have shown. So they connected, this is a this is, here there's a Raspberry Pi, and they connected a camera. So what they did is that they trained a model, and then they converted it into a TensorFlow Lite model, and then they deployed it onto this Raspberry Pi. So when this after that we can detect objects as well. Like initially they're trying to detect objects, and then this Raspberry Pi can detect objects as well. So there are many advantages here. Let's say if we want to make a simulation of C elegance, if let's say if we want to make a robot uh, which can which can model the movement of the C elegans. Then we can train the model, we can deploy it into a Raspberry Pi, and then we can instruct the Raspberry Pi to instruct its parts, like its wheels, to which direction it should move. Let's say if we put food near the robot, and if we can see the food, like how it can react. Basically we can do all the electronic stuff. Like this is a huge power to the electronic stuffs, because machine learning can be done in those small embedded devices only. And there's a specific use case for this also. Coca-Cola using this TensorFlow Lite model for digital marketing. So they had an app where uh, they want to take the images of a cap and see if the user, like if the buyer won any lottery or not. So instead of taking the image from the phone and sending it to the server, they took TensorFlow Lite, and then and there they have extracted that image, they have pre-processed it, then they have fed it into the model that has been deployed, and then the results have been deployed has been displayed. So this is how Coca-Cola has used this TensorFlow Lite. And TensorFlow Hub. This is also very powerful tool for us, because uh, with just one single line of code we can import pre-trained models. So in this under this link, there have been some pre-trained models hosted. Each of this model has a link associated with it. So whenever we want to use that pre-trained model, we can directly use model is equal to hub.module of that link, and then we'll be getting and then we can send our images into this module. Then we'll be getting features, and then we can we can train it on our own data set. Like let's say if we want to use the ResNet architecture, the ResNet has been trained on several classes. So what we can do is that the ResNet has been trained for thousands of hours on Google's GPUs, and it has gained those weights which can extract powerful features from the images. Like they can extract even the deepest features in those images. So we can make you, instead of retraining it ourselves, we can make use of that pre-trained model. So it has a link from tfhub.dev, and we can directly import those trained models with those weights, and then we can extract the features from our images, and then we can do the further training ourselves. Once the features are extracted, then we can send them into dense layers, and then we can map them into our classes of our own data set. So that's how this TensorFlow Hub is very useful for us, and it's also very easy to share. So suppose if I want to share my model weights to somewhere, I can just upload my model weights, and I'll be given a link. So whenever I give this link to someone else, they can use my model weights very easily. So these are these modules are nothing but TensorFlow Hub gives us modules, not the entire models. Like it need not necessarily be the entire model. It can be a module. A module is nothing but a subset of a model. Let's say the first 10 layers of a model can be called as a module. So we can use these. Let's say this is a module. We can fix it with our own code, and we can reuse them, and also we can retrain them also. So that gives us uh, a very powerful use case for us. So we can directly make use of those hours, thousands of hours and hours of training, and we can directly extract features from those from our data. And then there's TensorFlow datasets that has been introduced. So what this TensorFlow datasets does is that, let's say traditionally when we wanted to feed data into our model, traditionally what we would do is that first we would load the entire dataset into the main memory. We would pre-process it, and then we feed that into the model, right? So, but there is a problem here, because when the data set is very large, we cannot load the entire data set into our main memory, because so data sets can be of 20 GB or 30 GB of size, and the RAMs in our systems can only handle up to 32 GB or 64 GB if we consider a general system. So what this TensorFlow datasets will do is that it will generate the batches on the fly, instead of loading the entire dataset at once. So whenever we train a model, we train in batches, right? We will give a batch of data, and then we will give it to the model, and then the next batch comes, and so on, until every example in the data set has been done. We will call that as an epoch, right? So instead of loading the data set entirely at once, this datasets API helps us to generate these batches on the fly itself. Like when the model is training, we can generate a batch, and we can just load those for, let's say I have a batch size of 4. So I want 4 images only when I'm training a particular batch. So tf.dataset fetches those 4 like any 4 images as a batch, and then feeds it to the model, and then again it fetches the 4 images from the secondary memory to the main memory. This way, this dataset is being generated on the fly. Here's a small example that I have implemented. I'll try to explain why this is very useful in terms of GPU utilization as well. Because let's say in this train image names, this is a list actually. This is a list of image names, image 1, image 2, comma, image 3, image 4, image 5, let's say up to image 100. And these one hot labels, like this is for a classification task, right? So I was trying to do some classification task, and I wrote this code. Basically, in this train images names, I have it is a list of image names, and one hot labels is nothing but is nothing but the corresponding label for each of this image. So we can do this tf.data.dataset from tensor slices, and this dataset will like a new dataset object will be created, and then we are trying to shuffle the data, and then we are trying to map a pass function. Like now we have only these image names, right? Now we need to load those images from those image names, and we need to do some pre-processing as well. So in this pass function, I have written this code to load those images and resize it into a specific size. So in this dataset.map of pass function, when the code reaches this line, this pass function is invoked, and then those file names and labels will undergo into this process. And then also I used another function to pre-process those images that I wrote in this code. So basically the main magic comes here only. So when I say dataset is equal to dataset dot batch of 4, so then TensorFlow understands that, okay, you don't know, like then TensorFlow understands that we don't need the data, all of the data right at once. So we need these passing functions and train processes functions to be executed on our data set only on a batch of 4. Here the batch of 4 is nothing but 4 pairs of image and label, like image 1 label 1, image 2 label 2, image 3 label 3, image 4 label 4. So whenever I fetch a batch, that is what I will receive from this variable. And then there's this method called prefetch. Dataset.prefetch is nothing but when initially without pipelining, this is how the training would happen. This is the CPU, and this is a GPU or by TPU. This prepare one is nothing but like this is for one batch, second batch, third batch, fourth batch, fifth batch, sixth batch. So this prepare one is nothing but the pre-processing that has been going on for batch one. So when the CPU fetched the batch from the secondary memory, and when it is doing this pre-processing, the GPU will be idle, and when the pre-processing is done, that batch will be moved to GPU, and then the training will be started for that batch. During that time, the CPU is being idle. Like when the training is happening, the CPU is being idle, and then when the training is completed, then the CPU training for first batch is completed. Then the CPU fetches the second batch from the secondary main memory, and then it does the pre-processing again. And while this is happening, the GPU will be idle. So this is the case when we don't use pipelining. What this dataset.prefetch does is that when the GPU is training, the CPU will not wait until the GPU has finished training. It will directly fetch the next batch into that main memory, so that whenever the GPU has completed the training of that batch, the next batch will be ready to be loaded onto the GPU. So this TensorFlow Datasets API takes care of all this stuff under the hood itself. We only have to specify these things, prefetch and batch size or map functions or slices and all. And this initializer is nothing but by default these TensorFlow operations are not iteratable. Like we cannot iterate over them. So we can make them iteratable by this method, dataset.make initializable iterator. And whenever iterator got next is executed, like when next element is executed, the contents of next element will be 4 pairs of image and labels. 4 of image one label 1, image 2 label 2, image 3 label 3, image 4 label 4. And then we can directly use this next element, which is a batch of 4. We can directly feed it into the model to train. And while the model has been training, TensorFlow takes care of takes care of this pre-processing as well. While the training is happening, TensorFlow fetches the next batch immediately, so that the GPU will not have to wait until the next batch is processed. So that's how TensorFlow datasets is very useful for us. And yeah, I basically have that much to tell today. I want to give a small recap of what all I have told. First is the TensorFlow core, which enables us to build any kind of models. In that, there are sequential API for standard use cases, functional API for a bit more sophisticated use cases, and subclassing for highly advanced use cases. And then there's TensorFlow extended tool where we can get the model analysis, like complete model analysis, and also we can automate the workflow of right from the model, like data acquisition to uh, deployment. It can be a continuous process. And then we discussed about TensorFlow.js, and we discussed about how this enables real time prediction of models. And then also we discussed about TensorFlow Lite for mobile devices and embedded systems. And there's TensorFlow Hub, which we can use to fetch those pre-trained models. And then there's TensorFlow datasets to like create effective, efficient data pipelines. And yeah, that's all I have to say for today.
Well, it was very good. Thank you.
Yes, sir.
Yes, it was very complete. I like the overview of everything. Of course, for those of you who don't know, TensorFlow version 2 just came out recently, so that's why all the excitement around TensorFlow, and I think that's a very good educational resource. Can you post a link to the slides in the chat?
Oh, yes, sir.
Okay.
Yeah, definitely.
So Jesse and Ujwal had to leave early, so they said thanks for the great talk. They put it in the chat there. So I guess, yeah. So I guess what you're showing us is that there are a lot of different ways to do this. So that's sort of a platform that caters to a lot of different types of model, or it's basically one type of model, but it's a lot of different ways to implement it, and it gives you options on how you might, say, like build a pre-trained model or construct it.
Yeah, exactly. The best thing about TensorFlow is its ecosystem. Like there are multiple ways to achieve what we want to do. There's a like we just saw. TensorFlow.js enables us to do it right in the browser itself, and all of these tools are believed to be like give believed to give efficient performance. None of these will be lagging here and there. So active development has been going on in these tools. So I think TensorFlow, it's really great effort to put all these things together under one hood.
Yeah. Any questions? Anyone else have any questions? I don't know who's left here. Let's see. Abraham, do you have any questions? Okay. Well, yeah, I mean, let's see. I think I maybe had another question, but I can't remember what it is. Yeah, I think that's great. I'll post the slides for people to look over and see, to get a feel for TensorFlow. I think it's good to have it broken down like that so that you can see all the functionality. Oh, about the video game slide. You go back to that. So yeah, that's interesting because I used to work in a lab where we were doing psychophysiological measures and mapping them to controls on a computer screen. So people have done this with brain-machine interfaces, And like, you know, there's always been this real-time issue where you have to sort of train a model. This is sort of, you know, before machine learning became this huge field. You know, people were trying to figure out ways to train these models in real time so that you could take signals and figure out like effective states or like, you know, different movement controls. So you could like move a cursor with your mind in different directions, but you'd have to like decode brain activity to do that. So, you know, that real-time trainability is really important for a number of applications. And it looks like they
Yeah.
are doing going in that direction here. So it looks interesting. I don't know how good it is. I mean, there's a performance issue always with that sort of thing where, you know, if you're doing in real time, there's like individual variation, and then there's the ability to stream the data, you know, and then give feedback appropriately. So, but I think that's
Yeah, I do come across this performance issue when we train the models in real time in our browser itself. But it's an active issue right when the TensorFlow.js was announced. But from then onwards, many developers are working on that. And if we see now, we can see a huge change because previously TensorFlow did not support WebGL, which offers to render graphics or parallel processing very easily in the browser itself. So now it is supporting. So there might be a performance improvement. So I think like as the technology improves, we can actually get ahead of all those issues.
good. Well, thank you once again. So I guess everyone else left but Abraham and Vinay. So um, if Abraham is interested in presenting, he's welcome to do so at some point. So Vinay, you know, presented something that was fairly technical, and you've seen the presentations that I've given where, you know, they're a bit broader. So I mean, any kind of presentation is welcome. Uh, so you know, Abraham, if you're interested in contributing like that in that way, let me know. You know, it doesn't have to be next week, but it, you know, if we can just schedule a time and, you know, you just share your screen and go through slides. It doesn't have to be an hour long either. It can be like a 15-minute thing. So um, I just wanted to mention one more thing before we go, and that's this pre-trained model. So we had a conversation last week about pre-trained models, and it was pretty, you know, sort of general and thinking about like pre-trained models for biology. I was actually thinking of putting together a blog post that summarized, here he is, summarized some of this conversation. So let me show you what I have here. I've made this available in Google Docs. So this is the pre-trained model, sort of the outline of what we talked about last week. So let me go through it. So it would be like a blog post. It would be fairly short in terms of like writing. You know, it wouldn't be a paper length. It might be like 1,000 words or maybe 1,500 words. And so we might say something. We'll give it a better title than what is a pre-trained model. But we'll give it like 1,500 words of our attention. And then we have a number of different things under that heading. We have a short description, so, you know, to be able to discuss what a pre-trained model is, introduce it to people who don't know. Then point out that they're models for general use in specialized areas like languages, but not a huge selection of options specialized for biology. Then what specific use or interest is a pre-trained model to biologists. And I think we kind of talked about all those things. I haven't filled them in to this area, but it's something if we want to fill it in with, you know, if we have ideas of how to make this make this descriptive and readable, that's great. Problems for application of biology. So again, this isn't to be too long. You know, it's really me just put 1,500 words here. It's just like a very short description of like the types of problems you might have in applying this to biology. So the amount of input data or training data, what are the limitations? How would a pre-trained model solve our problems? Volume, which is a term, of course, I talked about in a previous lecture about data. So data volume is the size of the data set you need. Things like multivariate feature space, and then some discussion about models not equaling the phenomenon, but models as being this sort of heuristic. And then not customized for biological problems. So we assume that pre-trained models are universal, but that may not be true. Then maybe we'll, finish this with an example of modeling a biological image. So, some detail about how to model a biological image using a pre-trained model. Different things like blobs versus symbols. So I think Vinay brought that up, which is like using a symbolic approach or using like a data-driven approach where you're finding blobs or like shapes that are features. And so, we might talk about that as well. I haven't gotten too far on this myself, but I just wanted to show you a short outline of what I was thinking about for that. So if you're interested, I can, send you a link to the Google Doc, and you can contribute to the Google Doc, or, we can discuss it further. I don't really have a deadline on it, but, it's like whenever we can get around to finishing it. I think it would be a timely addition to the literature, at least in the blogosphere.
Yeah, sure. I'm on board.
Okay. So I'll send out that link, and then we can talk about it maybe next week in a little bit more detail. And that sounds good. Thanks. So Dick came back. Oh, anything else, Abraham?
Was it? Oh, not exactly. I will check my boss about my guess is I can do it. But
Okay.
I have to ask, of course.
That sounds good.
All
right. I think Dick came back, but then he went off screen for a minute. So I don't know if he had any questions about the TensorFlow presentation or. Okay. Well, anyways, I just wanted to